So, I think we have hit that hard enough. Let's go to my goodness, 4b5. It's Monday morning and it's early, believe it or not. Gravitational and electric potential energy. Let's first do gravity, and there is no friction. We have assumed no friction, no air drag of any kind. Here is the sun. It has a mass m sun. This symbol stands for the sun. Here's an object of mass little m at position 1 at separation r1 from the sun. And here is that same mass at position 2 at separation r2 from the sun. And I now want to evaluate the forces, gravitational forces, pulling from the sun. This is F1. It's radially pointing towards the sun, and the magnitude is m times the mass of the sun times g divided by r1 squared. And this force, which is smaller because it's farther away from the sun, F2, equals m times the mass of the sun times the gravitational constant divided by RT squared. And when I go all the way to infinity, F then at infinity, the gravitational pull from the sun equals 0, because 1 over r squared becomes 0. Now if I bring the object from position 1 to position 2, I have to overcome the gravitational force. So I move my hand to the right, I pull to the right, and I move it to the right, so I do positive work. And per definition, U2, that is the gravitational potential energy here, minus U1, the gravitational potential energy here, is per definition the work I do in moving that object from position 1 to position 2. And since here R2 is larger than R1, U2 minus U1 is larger than 0, so I do positive work. If I bring it from here to here, then R2 is smaller than R1, R2 minus U1 is smaller than 0, and U2 minus U1 is always larger than 0. But if I go from here to here, then I go from a higher potential energy to a lower potential energy, and so I do negative work. So I confused you, R2 is always larger than R1 in this case, U2 minus U1 is always larger than 0. If I go from 1 to 2, I therefore have to do positive work. If I go from 2 to 1, I therefore have to do negative work. I go from a higher potential to a lower potential. Now before we continue, I would like to examine with you a somewhat simpler case. Suppose here I have an object with mass m, and I have here a force mg, and here is my force Walter Lewin. I'm bringing it from, here is the floor, here's a tabletop. I call this tabletop arbitrarily y equals 0. I could have called this something else. This tabletop is at location A, this is at location B, and I bring it up to a position h, so y equals h here. Now to bring this mass from A to B, I have to do positive work. And per definition, UB minus UA is the work that I have to do to bring it from A to B. And it's immediately obvious that that is MGH. This is easy to remember. MGH stands for Massachusetts General Hospital. At least that's the way I always remember it. So that's the work I do when I bring it from A to B. Now here, since we are moving it at distances very small compared to the size of the Earth, the gravitational force is constant all the way when I go from A to B, so my force is constant, so that's why I can do it in this simple way. However, if we are going back to the problem with the sun, then of course the situation is somewhat different. If I go back to the sun, it is obvious that this force is not the same as this force. So now I cannot simply, when I do the integration in going from 1 to 2, I cannot assume that the force is constant. So F1 is not the same as F2 because R1 is smaller than R2. So now what is the work that I do? Well, that is the integral R1 to R2 of m sun times g divided by r squared dr. I go from here and I move it out, and I'm at some random location r, and I move it out over a distance dr. Over this small trajectory, I assume that the force remains constant. This is the magnitude of my force when I have to pull it to increasing value of r. So dr is positive here, and my force itself is also positive. I have to pull away from the center. You could call this force negative if you want that. Well, clearly I'm dealing here with a dot product between my force, Walter Lewin, and the r, but since the angle is 0 between the two, the cosine angle equals 1, so I can ignore that for now, and so I get that u at r2 minus u r1, which is the work that I have to do to bring the object from 1 to 2, becomes m sun times g times 1 over r1 minus 1 over r2. And I have assumed that there is no friction here. Now, if r2 is larger than r1, which is the case here, then this whole thing is larger than 0, and I do positive work. That's immediately obvious, because as I move the object farther away from the sun, clearly I have to overcome the gravitational pull, so it is immediately obvious that I do positive work, and so the potential energy at location 2 is larger than the potential energy at location 1. Now, what now is the potential energy at position 1? See, when you're dealing with very close to Earth situations in our laboratory, you can effectively choose the 0 level anywhere you want it. You can choose it on the floor, you can choose it at the tabletop, or you can choose it at that location B. Remember, I was moving it from the tabletop to that location B. It doesn't really matter. The 0 has no consequence. What counts in physics is the difference between potential energy. The difference between potential energy determines the force determines the acceleration, that means the change of velocity. So no matter how you decide, where you decide to choose your 0 gravitational potential energy in the laboratory system, the physics is not different. Here, however, it is meaningful and useful to choose that the potential energy of gravity at infinity equals 0. So I prefer that the choice is not yours now. Now the consequence of that is, if I fill in for r2 infinity, then I get r equals infinity, which we define to be 0, minus u of r. For r1 I put here now a random location r equals m, mass of the sun, times g, times 1 over r, because this is 0. This is a scalar, and this is 0, so if I rewrite this a little bit as ur, I get a minus sign here. So I get ur, gravitational potential energy, equals minus m sun times g divided by r. And it is a scalar, it has no direction. Let's put this in a nice red box, because it's a very important equation. This negative sign is the price that we have to pay for the fact that we call u at infinity equals 0. Put in r equals infinity and you see that u indeed becomes 0. If we wanted to draw a graph of the potential energy as a function of r, here is r, here is u potential, these values would all be positive, this would be 0, and these values would all be negative. Then the gravitational potential energy is a 1 over r, it's a hyperbole, so it would go like this, goes to 0 at infinity, but of course this is proportional, by the way, to 1 over r. But when you get inside the sun, then of course, if this is our sun, then this has to be reevaluated. This certainly does not continue as a hyperbole. And as r decreases, if r decreases, u decreases. For me, to move it further in, I have to do negative work. As r increases, u increases. Notice, even it is negative here, but it's still increasing. And for me, to move it further out, I have to do positive work. Now, if you know how u depends on x, y, or z, or r for that matter, you can easily find the vector components of the forces that are responsible for the potential energy. F of x, that is the x component of that force, equals minus du dx. What does that mean? I move the object only in the x direction, I keep y and z constant. And then I watch how the potential energy is changing. And this equation then gives you the x component of that force. Equally, Fy equals minus du dy, and Fz equals minus du dz. And if you have something that only depends on radius, like the case of the sun, Fr equals minus du dr. Let's take the situation of the table. On the table we had u as a function of y. Y was increasing in this way. Let's call it mgy. I then arbitrarily choose at y equals 0, I choose u equals 0. You are free to do this, but that makes it in this case rather easy. Well, if this is a scalar, if now I calculate the y component of the gravitational force, I get minus du dy, so I get minus mg. And this minus sign is simply telling you that it is in the opposite direction as increasing y. So this force is in downwards direction, which is exactly what it should be. Fx equals 0 and Fz equals 0, because there's no dependence of the potential energy on either x or z for that matter. Now the minus sign is also easy to see in the case of the sun, where we have only a radial dependence. The gravitational force would then be minus du dr. I have to do positive work to increase u. If du is positive, it means that dr is positive. I go outwards, and we all know that the gravitational force is directed inwards. That's the meaning now of this minus sign, just in a similar way as this minus sign was telling you that it is in the direction opposite to an increasing value of y. This is telling you that this minus sign is pointing in an opposite direction than increasing r. So the force of Walter Lewin, if I bring it out, would be plus du dr, because my force is exactly in opposite direction than the force from gravity. So u, in case of gravity, with the sun, equals m sum times g divided by R. Notice that when R increases, that U increases because of this minus sign. Now the U dr equals plus m sun times g divided by r squared. So F in the radial direction of gravity is minus the u dr. So F in the radial direction equals minus m sun g divided by r squared. And the minus sign then indicates that it is pointing in the opposite direction as increasing r. I prefer a different notation. If here is the sun and here is r, I would like to introduce, but I think Professor Goose is not doing that, I would like to introduce a unit vector r roof. It has length 1 and it is radially pointing out. And I would like to put here an r roof and here a vector. Then there is simply no confusion whatsoever. You see immediately that the gravitational force is opposing the unit vector r roof, which is pointing outwards to increasing value of r. But this is a matter of taste, and I leave it up to you what you prefer. Now we turn to electric potential energy. Now we have a charge plus Q and plus capital Q. And unlike gravity, these repel. So already you feel in your stomach that everything is going to be very, very similar, except that minus signs may change to plus signs and plus signs may change to minus signs. Yeah, that's true, but remember, in electricity, the charges can also have opposite signs. And if that's the case, they attract each other. So then you would expect to see something extremely similar to what we have seen with gravity. Because with gravity, masses cannot be negative and positive, so with gravity we always have attracting forces. All right, here we have plus Q, and here we have plus capital Q. They are at a distance r, and they repel. So the electric force is in this direction, outwards, and the electric force here equal in strength in opposite direction. And the magnitude of this electric force equals Q times Q divided by 4 pi epsilon 0, something you will see later in 802. It's a constant, divided by r squared, inverse r squared. If I increase the distance between these two objects, I have to do negative work. If I have to bring them closer together, I have to overcome this repelling force, then I have to do positive work. And if again I assume that the potential energy at infinity is 0, I now get that the electrostatic potential energy, not gravitational but electrostatic, equals plus Q times capital Q divided by 4 pi epsilon 0 r. This is nearly identical to gravity, except that with gravity we had a minus, and here we have a plus. But now, the nice thing about this equation is that if you change the signs of Q and capital Q, little q and capital Q, if you make them both negative, the plus sign still remains plus. Because minus times minus is still plus. So this still holds. If, however, they have opposite signs, either this plus and this minus, or this plus and this minus, then the upstairs here becomes negative, and you get a situation which is completely analogous to gravity, which is exactly what you predict, because now you have attracting forces. And when you have attracting forces, the upstairs here, once you make this multiplication, the upstairs become negative. So it's very nice and very cute that you see here the beautiful symmetry with gravity in case that the electric charges attract each other.